Now power efficiency of transformer. It is known that efficiency is equal to output power by input power. So which can be taken as equal to output power by output power plus losses, because input power can be taken as equal to output power plus losses. And in case of transformer, efficiency is defined as the ratio of output power by output power plus losses, and here output power is given by X into kVA rating of transformer into power factor. This is output, okay, and output plus losses. So X into kVA into power factor plus losses are iron losses and copper losses. So X square into WCU, where here X represents the load, that is for full load X is equal to 1, and for half load X is equal to 1 by 2, and for 1/4 of full load X is equal to 1 by 4, and so on. Now let's find out the condition for maximum efficiency. For that we need to differentiate this equation with respect to load current at constant power factor and equate to 0. And here kVA rating is constant, power factor is constant, iron losses are constant, and the losses which are variable with respect to load current are copper losses. So if you differentiate this with respect to X into I2, that will give you WCU is equal to WI. Means the condition for maximum efficiency is copper losses equal to iron losses. And please keep in mind that we shouldn't write WI is equal to WCU. This is wrong representation. The correct representation is WCU is equal to WI, because if suppose constant loss is 50, that is WI, and with respect to load the copper losses will vary. So let us suppose at a particular load the copper loss is 20, and similarly for another increased load that the copper loss be 30 and the iron loss will be 50 because it is constant, and for further increase in load that the copper loss be 50 and the iron loss will be 50 because constant loss, and for further increased load copper loss will be, let it suppose 60, and iron losses will be 50. So if you observe that copper losses is variable loss, but at a particular load it became equal to iron loss. So we must represent copper loss equal to iron loss, but not iron loss equal to copper loss. And in this case copper loss is equal to X into I2 whole square into R02, and which is equated to WI. That implies X square I2 square is equal to WI by R02, and which implies X square is equal to WI by I2 square R02. And here with I2 there is no X, which represents here full load copper losses. So WI by WCU full load, and that implies X is equal to square root of iron losses by full load copper losses. This is one more important relation which will represent the load at which maximum efficiency occurs. Next let's consider X into I2 be I2M, which implies I2M is equal to square root of WI by R02, and this is the one more important relation which will indicate the load current at which maximum efficiency occurs. This is the load at which maximum efficiency occur, and this is the load current at which maximum efficiency will occur. And now multiply on both sides with E2. So E2 into I2M, which is equal to E2 into square root of iron losses by R02, where here R02 is the equivalent resistance of transformer. And now divide and multiply this with I2 and take this I2 inside square root. So E2 into I2 divided by Wi by I2 square R02, and I2 square R02 represents the full load copper losses. So Wi by WCU FL. So now if you observe, this represents the kVA rating, E2 into I2, and I2M represents the load current at which max efficiency occurs. So this is the kVA rating at which max efficiency occur is equal to, this is kVA rating at full load. So kVA rating at full load into root over iron losses by full load copper losses, and this is another important relation. So in numerical problem, if iron losses and full load copper loss are given and it is asked to find the load at which max efficiency occurs, use this equation, and if it is asked to find the load current at which max efficiency occurs, use this, and if it is asked to find the kVA at max efficiency, use this equation. Therefore, the condition for max efficiency is copper losses equal to iron losses. Therefore, total losses can be taken as equal to 2 into iron losses, because copper losses is equated to iron losses, means in place of this you must keep Wi. So which will give you total losses Wi and Wi, means 2 Wi. And now if you differentiate the efficiency equation with respect to power factor at constant load current, the condition which we get is cos phi 2 is equal to 1. Means if you maintain the load current constant, then max efficiency will occur at unity power factor. That is, if suppose this is the efficiency and let us suppose this is the power factor, and let this be the unity power factor here. So efficiency will be maximum at unity power factor. That is, we will get max efficiency at unity power factor if you maintain the load current constant. Now let's have the important discussion on the difference between power transformer and distribution transformer. From this you will know what power transformer is for and what distribution transformer is for. Power transformers are used in transmission network, whereas distribution transformer is used in distribution network, and power transformers rating generally will be greater than 1 MVA, and distribution transformers rating will be less than 1 MVA, and voltage ratings will be greater than 33 kV, and whereas in case of distribution transformers voltage ratings will be less than 33 kV. And the other point is here that power transformer is indirectly connected to load, whereas distribution transformer is directly connected to load, which means load fluctuations effects are more in case of distribution transformer, whereas in case of power transformer load fluctuations effect is less. And the fourth point is it is 24 hours loaded, whereas loading on distribution transformer depends on load cycle. This is the important point from which we will derive few more points. As the power transformer is 24 hours loaded, so copper losses and iron losses present for all 24 hours, whereas here iron losses present for 24 hours but copper losses depends on load cycle. because copper losses depends on the load current. And in case of power transformer, as the power transformer is loaded for all 24 hours, means there are copper losses and iron losses present for the whole 24 hours. Whereas distribution transformer is loaded according to the load cycle. So when there is load connected, then there will be copper losses. But for all 24 hours, the primary of distribution transformer is excited, means iron losses present for all 24 hours. But copper loss is present only when load is connected. So in designing transformer, importance is only given to reduce the iron losses, and importance is not given to copper loss, because copper loss is present or not present, that depends on the load cycle. So in designing, importance is given to reduce iron losses. Therefore, low magnetic flux density material, amorphous silicon steel is used for core. And coming to power transformer, as the power transformer is continuously loaded for all the 24 hours, so the iron losses and copper loss are also present for all the 24 hours. Therefore, here in designing, importance is given to reduce copper losses. And here for core, the material used is CRGO steel, and CRGO steel will have good flux density. And the other important point is, as the power transformer is 24 hours loaded, means the average load is full load, because it is continuously loaded for all the 24 hours. So here X is equal to 1, that is maximum efficiency occurs at X is equal to 1. And coming to distribution transformer, here loading depends on the load cycle, and the maximum efficiency will occur at around 3/4 load. And we have a relation that X is equal to root over iron losses by WCU full load losses. And if you place X is equal to 1, which implies WCU full load is equal to WI. This is the condition. And whereas in case of distribution transformer, WCU full load will be approximately equal to 2 times WI. Performance of power transformer depends on power. Therefore, the efficiency here is power efficiency. Whereas in case of distribution transformer, performance depends on power and time. Therefore, efficiency is all-day efficiency, which is represented like this, which is equal to output energy divided by output energy plus energy losses, and which is in kWh. This is kWh, and this is also in kWh. Now let's understand this with a numerical example. And this is the numerical example for which we need to find the percentage all-day efficiency. So here it is given that a 400 kVA distribution transformer, which is having iron loss of 2.5 kilowatts and a full load copper loss of 3.5 kilowatts, and this is the load cycle for 24 hours. And using this data, we need to find percentage all-day efficiency. To understand this problem, let's elaborate this formula, which is equal to output energy in kWh by output energy, that is in kWh, plus energy losses. Energy losses are iron losses and copper losses, which are equal to X square times WCU in kilowatt hours. And if you observe this formula, that here we need to first find the X, because here there is no information about X. So consider first row. So here 6 hours 300 kilowatts and power factor is 0.8, which implies if you multiply this we will get in kVA, that is equal to 240 kVA. Therefore, the loading on transformer for this whole 6 hours is 240 kVA divided by rating of the transformer. That implies X is equal to 0.9375. And similarly, find the loading on transformer for these 10 hours. So for these 10 hours, the transformer output is 200 kilowatts at 0.7 power factor, which implies in kVA it is 200 into 0.7, which is equal to 140 kVA. Therefore, the loading on transformer is 140 divided by rating of transformer, that is equal to 0.714. And similarly, find X for these 4 hours, and for next 4 hours there is no loading, so there is no need to find the X. And here we are finding the all day efficiency for 1 day. Therefore, output energy for first 6 hours is 6 into 300 kilowatts plus output energy for next 10 hours. So 10 into 200 kilowatts plus output energy for next 4 hours. So 4 into 100 kilowatts divided by output energy for the whole 24 hours is this one. So repeat the same plus, and here comes the important point that you must keep in mind, that is about iron losses, whether the transformer is loaded or not loaded. Distribution transformer iron losses are present for whole 24 hours. So here you must keep 24 into iron losses, which is 2.5 kilowatts. And next, now consider the copper losses for this entire load cycle. Copper losses depends on the load, so for different loadings, copper losses will vary. And here for first 6 hours we found the load X is equal to 0.9375. So for first 6 hours, 6 into 0.9375 whole square into full load copper loss is 3.5 plus, and for next 10 hours we found X is equal to 0.714. So for next 10 hours X square is 0.714 whole square into full load copper loss is 3.5 plus, and for next 4 hours we found X is equal to 0.27, something like that. So 4 hours into X square is 0.27 whole square into full load copper loss is 3.5 kilowatts. And by solving this you will get around 97.73% like this. So this is how we need to find percentage all day efficiency of distribution transformer by using this load cycle data. And please keep in mind that here first we need to find the X, and using that X we will find the copper losses for different durations. Next, voltage regulation, which is defined as the ratio of no load voltage minus full load voltage to the no load voltage. That is, in case of transformer, no load voltage is induced voltage E2 and full load voltage is the terminal voltage V2, and the ratio and no load voltage is here E2. So percentage voltage regulation, which is represented with R. So percentage R is equal to E2 minus V2 by E2 into 100. If suppose this is the schematic diagram of transformer, and if the primary parameters are transferred to the secondary side, then this will represent the schematic diagram of the transformer. And if primary voltage is transferred to the secondary side, that is represented with E1 dash, and that is equal to K times E1, and the terminal voltage is here V2. If suppose now there is no load, when there is no load, then the terminal voltage V2 is equal to E2, but when load is connected, then there will be current in the secondary. and because of which now there is an impedance drop, and as there is impedance drop, now V2 will be less than E2 because of impedance drop. So we can take the difference of E2 and V2 as I2 Z02. If suppose now load on the transformer is increased, if load on transformer gets increased, then the secondary current in the secondary circuit will increase. If secondary circuit current increases, then the impedance drop will get increased. If this gets increased, then the terminal voltage available at the terminals of transformer is not sufficient to those loads. And as the loads are designed to operate at a particular voltage, and if those loads are not getting the sufficient voltage, then the loads will not operate to what they are expected to do. Therefore, the main task of transformer is to provide the sufficient voltage levels to the load. But if the loads of transformers are increasing, then the impedance drop is increasing, and because of which the terminal voltage available at the terminals of transformer is decreasing. So here there comes the restriction of load on the transformer. That is, the load on the transformer can be increased till a particular value of terminal voltage, and beyond the particular value of load, the terminal voltage available from the terminals of transformer is not sufficient to these loads. And from this discussion, you must understand that we require this impedance drop as minimum as possible. That is, we require this difference as minimum as possible. And if you observe this formula, percent regulation is equal to ratio of no load voltage minus full load voltage by no load voltage, and percentage regulation is directly proportional to change in voltage, and we require this change in voltage as minimum as possible. That implies we require percentage regulation as minimum as possible, and a good voltage regulation transformer means the percentage regulation value is very low. Now let's derive the formula for percentage voltage regulation, and for that let's use this secondary circuit. And now to derive the equation for percentage voltage regulation, let's consider this part of the phasor diagram of transformer. And if terminal voltage V2 is taken horizontally like this, then the secondary current is I2, and the angle between V2 and I2 is phi 2. And from this circuit you can note that E2 is equal to I2 Z02 plus V2, means to get E2 we need to add I2 Z02 drop to the V2, and I2 Z0 drop is I2 R02 drop plus J I2 X02 drop. So to get E2 we need to add these two to the V2. So first let's add I2 R02 drop to the V2. So I2 R02 drop will be parallel to the I2 phasor. So this represents the I2 R02 drop. And now let's add this drop to the V2, and this drop will be perpendicular to the I2 phasor. So maintaining perpendicular with I2 phasor, let's draw the I2 X02 drop, and now the resultant is E2. And here our task is to find the difference between E2 and V2. For that we are considering this portion of phasor diagram from this phasor diagram of transformer. Now extend this horizontal line like this, and project the E2 along horizontal axis. So if you observe that from this portion to this portion it represents V2, and from this portion to this portion it represents E2, and from this portion to this portion it represents E2 minus V2. So if you can find E2 minus V2, then we can submit this here, and then we can find the formula for percentage voltage regulation, and this angle is phi 2. And now observe that to this horizontal line this is the perpendicular line, and to this line this is the perpendicular line. So if the angle between this line and this line is phi 2, then the angle between the perpendicular lines drawn from these lines is same, that is here phi 2. And now if you project the I2 R02 drop along horizontal axis, that will represent I2 R02 cos phi 2. And if you project this I2 X02 drop along horizontal axis, that will represent I2 X02 sin phi 2. Therefore, E2 minus V2 can be equated to I2 R02 cos phi 2 plus I2 X02 sin phi 2. Therefore, the formula for percentage voltage regulation is equal to I2 R02 cos phi 2 plus I2 X02 sin phi 2 divided by E2 into 100. And this is the percentage regulation formula for lagging loads, because we considered here lagging load, and for leading loads here in place of plus we will get minus. So plus for lagging load and minus for leading loads. And if you observe that I2 R02 by E2 into 100 represents the percentage resistance drop, and simply it is termed as percentage resistance. So that is equal to percentage resistance into cos phi 2 plus or minus, and here I2 X02 by E2 into 100 represents the percentage reactance drop, and simply it is termed as percentage reactance, and percentage reactance into sin phi 2. This is one more formula for percentage voltage regulation, where percentage resistance is equal to I2 R02 by E2 into 100, and percentage reactance X is equal to I2 X02 by E2 into 100. And now let's find out the conditions for maximum voltage regulation and minimum voltage regulation. First, let's find out the condition for maximum voltage regulation. And maximum voltage regulation is obtained at lagging loads. So here consider the plus sign. So percentage regulation is equal to percentage R into cos phi 2 plus percentage reactance into sin phi 2. And now to get the condition for maximum voltage regulation, differentiate this with respect to power factor angle phi 2 and equate to 0. So differentiating percentage regulation with respect to power factor angle phi 2 and equating to 0, which implies differentiation of cos phi 2 is minus sin phi 2 and differentiation of sin phi 2 is cos phi 2. So which implies tan phi 2 is equal to percentage X02 by percentage R02, and which is equal to X02 by R02. Therefore, power factor angle cos phi 2 is equal to R02 by Z02. So if this is phi 2 and tan phi 2 is opposite side by adjacent, so opposite side is X02 and adjacent side is R02, and the resultant is Z02. And now cos phi 2 is equal to adjacent side by hypotenuse, so R02 by Z02. And now from the impedance of transformer, this is R02 and X02, that is R02 and X02, resultant is Z02, and impedance angle is represented with theta 2. That implies tan theta 2 is equal to X02 by R02. And now by comparing this with this, it will imply that tan phi 2 is equal to tan theta 2, which implies the condition for maximum voltage regulation is phi 2 is equal to theta 2. Variable angle must be equated to constant angle. Theta 2 is equal to phi 2 is the wrong representation, and the correct representation is phi 2 is equal to theta 2, variable and constant. Phi 2 is load power factor angle and theta 2 is transformer impedance angle. And now by comparing this with this, it will imply that x by r ratio of load is equal to x by r ratio of the transformer. This is one more important relation. Let's consider the ideal case. And ideally, the resistance of transformer is 0, which implies theta 2 is equal to 90 degrees. But practically, resistance is not equal to 0, which implies theta 2 practically will be around 80 to 85 degrees. The condition for maximum voltage regulation we got phi 2 is equal to theta 2, which implies power factor angle is equal to 80 to 85. That implies power factor is around 0.1, 0.2, etc. That implies that maximum voltage regulation will occur at low power factors. Therefore, for lagging loads, if suppose this is the percentage voltage regulation, and let us suppose the power factor, lagging power factor angle, and let the center be unity power factor 1, and if you take this 0.8 and so on, and let us suppose this is the 0.1, and it is discussed that maximum voltage regulation occurs at low lagging power factors. So let this be the maximum voltage regulation at low power factors. So the graph will be like this. Therefore, for maximum voltage regulation, we got cos phi 2 is equal to R02 by Z02, and tan phi 2 is equal to X02 by R02, and phi 2 is equal to theta 2, and x by r ratio of load is equal to x by r ratio of transformer. We have percentage regulation is equal to percentage resistance drop into cos phi 2 plus percentage reactance drop into sin phi 2, and this can be taken as equal to percentage resistance drop by percentage impedance drop. That implies percentage resistance drop R02 into cos phi 2 is percentage resistance drop by percentage impedance drop plus percentage reactance drop into sin phi 2 is percentage X02 by percentage Z02, and that implies percentage R02 square plus percentage X02 square by percentage Z02, and this will represent the percentage Z02 square by percentage Z02. That implies percentage voltage regulation is equal to percentage Z2. This is one more thing that we obtained from the maximum voltage regulation, that is maximum voltage regulation is equal to percentage impedance. And now let's derive the conditions for minimum voltage regulation, and minimum voltage regulation is obtained for leading power factors. So let's consider the formula. Percentage regulation is equal to percentage resistance drop into cos phi 2 minus percentage reactance drop into sin phi 2, and minimum voltage regulation means 0, so that is equal to R02 cos phi 2 minus percentage reactance into sin phi 2. That implies tan phi 2 is equal to percentage R by percentage X. That can be taken as equal to R02 by X02, and which implies power factor angle phi 2 is equal to percentage X02 by percentage Z02, or that can be taken as equal to X02 by Z02, and that is from the triangle, as tan phi 2 is equal to opposite side by adjacent side. So here opposite side is R02 and adjacent side is X02 and the resultant is Z02, and from this we are obtaining cos phi 2, which is equal to adjacent side by hypotenuse. So adjacent side is X02 and hypotenuse is Z02. So this is the one condition obtained in minimum voltage regulation. And now consider the impedance of transformer, so which implies this is impedance angle theta 2 and this is impedance Z02, this is reactance X02 and resistance R02, and that implies tan theta 2 is equal to X02 by R02. Tan phi 2 is equal to R02 by X02, but tan theta is equal to X02 by R02, which implies tan phi 2 is equal to 1 by tan theta 2, and we know that tan theta is equal to 1 by cot theta. So now let's represent this in terms of cot. So cot 90 minus theta 2, which means as here theta is equal to theta, and that implies phi 2 is equal to 90 minus theta 2. So phi 2 is equal to 90 minus theta 2. That implies phi 2 plus theta 2 is equal to 90 degrees. This is one more condition. And now observing tan phi 2 and tan theta 2, which implies x by r ratio of load is equal to reciprocal of x by r ratio of transformer. This is one more important condition. Therefore, consider ideal case and then practical case, and we know that ideally resistance is equal to 0, which implies theta 2 is 90 degrees, but practically R02 is not equal to 0. That implies theta 2 is equal to 80 to 85 degrees. And the condition for minimum voltage regulation is phi 2 plus theta 2 is equal to 90, and we have theta 2 practically is 80 to 85, which implies phi 2 is equal to 90 minus 80 to 85 degrees, which implies phi 2 will be around 10 degrees to 5 degrees or etc. That implies power factor angle cos phi 2 will be around 0.9, 0.8, etc., which means we will get minimum voltage regulation at high leading power factors. Therefore, the percentage regulation graph of transformer will be like this. If origin represents the unity power factor and the scaling be like this, and similarly 0.9, 0.8, 0.7 and so on. And it is discussed that maximum voltage regulation occurs at low lagging power factors. Means let us suppose this is the low lagging power factor, and we have percentage regulation is equal to percentage R cos phi 2 plus or minus percentage X sin phi 2, and at unity power factor means at cos phi 2 is equal to 1, sin phi 2 is 0, so which implies percentage voltage regulation at unity power factor is percentage R. So at unity power factor, let the percentage regulation be this. Means now the graph will be like this, and maximum voltage regulation we got percentage Z, and we got cos phi 2 at maximum voltage regulation is percentage R by percentage Z, and it is known that minimum voltage regulation is 0, and that is obtained at the higher leading power factors. So let this be the 0 voltage regulation, and which is happened at higher leading power factors. And here the power factor angle is cos phi 2 is equal to percentage x by percentage z, that is x02 by z02. Therefore, this is the graph of percentage regulation of a transformer. And please make a note that we require good performance of transformer, that is percentage voltage regulation must be good. If percentage voltage regulation good means the percentage regulation value is low, that is we require low percentage regulation, and percentage voltage regulation will indicate that low impedance drop, that is the terminal voltage available to the loads from the transformer is sufficient. And the efficiency curve for transformer is seen like this. The efficiency curve of transformer is called as double valued function because for different loads, that is for two different loads, the transformer will have same efficiency. And one important point that you must keep in mind here is that for same power factor, in case of lagging loads, efficiency is slightly more than the efficiency at leading loads. If suppose 0.9 is the power factor, then efficiency of 0.9 lagging power factor is slightly more than the efficiency of 0.9 leading power factor.